Homework 1 is about solubility curves. So this is very similar to the solubility curve that you made for sugar. This one just shows many different solutes on one graph. So the first few questions are about KClO3. So I'm going to go ahead and highlight that line so it's a little easier to see here. So as temperature increases, the amount of KClO3 that can be dissolved also increases. So at 20 degrees, the amount of KClO3 that I can dissolve is going to be 10 grams in 100 grams of water. So if we are right on the line, that corresponds to a saturated solution. If we add any amount less than 10 grams at 20 degrees, we're going to have an unsaturated solution. So anything below the line is going to be unsaturated. On the line is saturated. If we have more than 10 grams, so that's anything above the line, that solution would be supersaturated. So at 20 degrees, the amount of KClO3 that can be dissolved in 100 grams of water is 10 grams. So we just saw that on our graph here. So how much solute would dissolve in 50 grams of water? So if we have half as much water, we can dissolve half as much KClO3. So we would only be able to dissolve 5 grams. What if we double the amount of water? If we have 200 grams of water? Well, if you have twice the amount of water, then twice the amount of solute will be able to dissolve. So here we would get 10 times 2, which is 20 grams of KClO3. Consider the solubility for potassium chloride. So we're going to find potassium chloride here. And we want to know what is the solubility at 10 degrees. So that looks like that's right around 30 grams. And at 80 degrees, that looks like it's a little bit above the 50 mark to me. So I'm going to say 51 grams. So according to my key here, a solid line, like we have for KCl, indicates to us that this is a solid. So what happens to the solubility of solids as temperature increases? So the solubility also increases. And this is true for most solids. So for example, when you're making your sweet tea, you dissolve the sugar when the water is still warm, when the tea is still warm, because it will have a higher solubility. You don't put the sugar in when the tea is already cold and has ice cubes in it, because then you're going to have a really hard time getting it to dissolve. Next question says to consider the solubility of ammonia, NH3. So that's this guy right here. So what is the solubility of ammonia at 10 degrees? So that's right around 70 grams. What would be the solubility at 50 degrees? That looks like around 30 grams. And according to my key here, ammonia has a dotted line, so that means that ammonia is a gas. So what happens to the solubility of gases as temperature increases? So if the solubility curve is showing this negative relationship here, that's telling us that the solubility decreases for gases. And this is generally true of all gases. If you raise the temperature, the solubility will decrease. So at 90 degrees Celsius, 10 grams of KClO3 is dissolved in 100 grams of water. Is this saturated or unsaturated? So at 90 degrees, if we look and find KClO3 at 90 degrees, it can hold right around 50 grams or about 51 grams of KClO3. So we've only added 10. 10 is much less than 51. So this is telling me that my solution is unsaturated. In fact, I could add up to another 41 grams and still be unsaturated. Once we have a total of 51 grams, the solution would be saturated. Anything above that would be supersaturated. A saturated solution of potassium chlorate is dissolved in 100 grams of water. If the saturated solution is cooled from 90 down to 60, how many grams of precipitate will be formed? You could also, instead of precipitate, you could think of crystals. So we need to figure out how much KClO3 can be dissolved at 90 versus at 60. So at 90 degrees, we said just a little while ago that it was 51 grams of KClO3. So then let's check what it is at 60 degrees Celsius. So at 60, this looks like it's just a hair below 30. So I'm going to say that that's 28 grams of KClO3. So at 90 degrees, I can hold 51 grams, and at 60, I can only hold 28 grams. So the difference between these two numbers, 51 minus 28, will give me the amount of crystals that we would expect to see in the bottom of the beaker. So if I took my solution at 90 and saturated it with KClO3, and then I allowed it to cool to 60, I would expect to see 23 grams of potassium chlorate, KClO3 crystals forming in the bottom of my beaker. So question 11, carbon dioxide gas, CO2, is dissolved in bottled soda under high pressure. So what will happen to the dissolved CO2 in the soda if the cap is removed? So when we want to dissolve CO2 into water, we do that under pressure. So when we remove the cap on the soda, there's nothing maintaining the pressure over the soda, nothing to keep the CO2 from bubbling out. So the CO2 starts to bubble out of the solution. So pressure is used to force CO2 into the liquid soda. We can't do this by increasing the temperature. Like if we were talking about dissolving sugar into tea, we could just raise the temperature to get that sugar to dissolve. But with CO2, if you raise the temperature, gases become less soluble. So I have to use pressure instead to force the CO2 into the soda. So compare two open cans of soda. Can A is at room temperature and can B is in the refrigerator. Which one will go flat first? So carbon dioxide is more soluble in the cold soda. So can B will take longer to go flat. When soda goes flat, it really just means that the CO2 has escaped and the soda solution is no longer bubbly. So at higher temperature, out on the counter at room temperature, carbon dioxide will escape the soda faster in can A.